Hello. Hello. Yeah, okay, thanks. Now, everyone, so we are moving to another chapter. But before that, last time you remember that we were working on the linked list. Now, for the linked list, we see that they have some advantages over the array. Means that we can insert, delete in a one. Okay, and we agree with each other that this is just very easy. Just move the pointer and then we can have a new item in place without shifting, moving anything. Of course, if we move it to deeply linked list, the logic for the insertion and deletion is a bit higher, as we need to manage many pointers in the same time. But anyway, that will be O1. Okay, so it's good. And we remember that I asked you to play with the soft algorithms on the linked list. No, means that we want to apply the basic sorting algorithms to the linked list. Then the answer should be we can do it. It should not change any algorithms. Okay, means we can do the comparison, we can do the swapping, we can do the insertion as we want. Okay, so you see, remember, insertion sort, purpose sort, or selection sort, all of them are feasible in. It means we can do it in the linked list. Okay. So a linked list is a good alternative for array. Okay, that is what we know so far from the linked list. There is one question I want to ask you. Can you tell me on the size of the linked list? Okay. What will be the size? It means the maximum number of items we can store in a linked list. What will be the maximum number of items that we can store in a linked list? It is. Yes. You see, because what? Why it depend on the memory of the computer? Yeah, because every time we want to add a new item to the linked list, we just create a new item. As long as we can create a new item, means we still have memory for our software, we can add a new item to that list. Okay, it's different from the array. No, the array, they have a fixed size. We have to ask the system to allocate a set of memory next to each other for us. Okay, but for a linked list, it could be anywhere, and we just add a new item somewhere in memory and link it to the linked list. That's it. Okay, so you see some advantages of the linked list like that. Okay, now we are moving to another topic that I think many of you know it in C programming, or you know it somewhere else. So it's the recursion. Okay, so what is the recursion? So that should be very clear for everyone. Is that we have some introduction to recursion and why we have it, and we have some example, and we see what we can do with recursion. Okay. We have one example of the sorting algorithm using recursion. Okay. So recursion is a way that we solve a problem by apply the same techniques again and again with a smaller size. Means in order to solve the big one, we have the smaller one, and until some very basic step, and then we can solve it. And just here a bit more detail. So there is one example. We call it triangular numbers. Means we have the definition of that triangle. Means for the first triangle that we have one element only, and the second we have three elements. But what people can say is that the second element is the first element plus here the plus 2. That is what we have. Okay, so just one second. Okay. So here, and the third element will be the second element plus 3. The fourth element will be the third element plus 4, and so on. Okay, so by that way, people can define the triangle numbers. And the question maybe later on is, I want to check how many items do we have for 100 element of that triangle numbers. Okay, of course what we can say is that will be 100 plus the 99 element, and then so forth. And in that way, if people have to implement a function to compute the number of elements in square in that triangle, we can always do the while loop. No, really quite basic. So y and bigger than 0, we do total plus total n. Okay, or we can define it in a recursive way, as you hear, is that the triangle n will be the triangle n minus 1 plus n. Okay, of course we say this is an incomplete version of the function because we miss any function that call itself. We call it recursive. Yeah, it call itself recursive. And there's one thing that you should remember: the parameters. It means the problem we ask the system to solve again somehow should be changed. It means smaller or bigger. It should not be the same. Okay, and in any recursive method, we have two parts. This part we call it recursive part. When we call it cell, we have recursive part, and this one we call it the base case. Means this is where we know exactly what to do without calling the triangle or function again with the smaller parameters, because it is straightforward. Here, if the number of elements is 1, we know it immediately without asking anyone else. We know it is 1. Okay. If it is 10, we don't know. We should say 10 plus something. Okay. So now my question for you first is, why people use recursion? In this case, we have two versions. Like the one is the while loop, and another one is the recursion. Okay, so it means people can do it in either ways here. But can you tell us why people want to use recursion here? Not in this specific situation, but why people want to use recursion? That is the question. Why is that? Yeah, we know recursion is we need to do something over and over again, but we can always do it with the for loop, no? Because the instruction in the method is constant in running time. So it's better than in the loop. Everyone else, is it the case? Everyone, do you agree that for the triangle function here, the complexity is 01? Yeah, I don't say anything about it's better, no? And in this case, the triangle function is not better. That is not 01 in any sense. Okay, it is still on. Okay, the code just sampler. The answer is not totally correct. Means that in some situation we see the code of the recursion or recursive method sampler. In some other case, it's not that sampler. Okay, actually it depends on the problem. Okay, but let's have a look at this one. I will try to say the first thing I want to tell you is you should remember that the recursion is inefficient. The recursion is not good for performance. Okay, it runs slower than the interactive version. Okay, here some explanation. Have a look at this. We have this one is a call of the triangle function with the input in number 5. Okay, so when we call it 5, what we do here is we go to, if not 1, we go here. We say 5, triangle of 5 will be triangle 5 plus the triangle of 4. Means we will call the second version of the function with any 4. There is a thing that you should remember. When we have to call a function again in our system, the memory have to allocate memory for the variable n as the input parameters of the function. This means we have make a new version of that. Okay, we have to keep track of the address of this function, and we have to keep track of the address of this position. This means where should we return? Means the system have to make a new version of the function, have to duplicate all of the parameters used in the function. Okay, and add one new variable to keep track of the return position. Where should I return? Okay, from 4 I will return to 5. Okay, and in 4 we do it recursive call again. So we make another version of n equal 3, another version of the function. I'll keep track of the memory and so forth until we reach n number 1. We have nothing else to do. We just simply return, and then we go back. You see, up from 5 to 1, we have to keep track and store everything from the top to this core base case is 1. After we finish with that, we return 1. We can remove this function. It's been the memory for the function now because we had the result, and we get that result. We go to 2. After we have 2, we return 3, and then we can remove the memory, the storage, the variables, everything related to this version 4 with n equal 2, and so forth. This means only after we finish with that, we can release the memory. Means that if we have to call the recursive function 1000 times, we had to make 1000 copy of that variables and 1000 extra variables to store the return address of everything. Okay, and of course in the memory in the system we have a stack, we call it call stack, that show us where to do things. And you see that this is why recursion is not good. Okay, it takes a lot of work for the system. We have to duplicate things, we have to store a lot more than that. Okay, so up to this, what we can say is recursion is not good in terms of performance. Okay, and now I back to the question again. Other than performance, why do people want to use recursion? My answer is people don't want to use recursion. People don't want to use recursion. We use recursion because we have to do it. People force us to do it, and we try to avoid it. One of the reasons why we have to do it is we don't know how to do it in the iterative way. Recursion will not help you to manage the code easier. No. Okay. Recursion have many problems. Okay. We use it because we have to use it. In other words, we have no choice. Okay. So if you have the way to solve the problem in the iterative way, do it. Okay. Or in some case, it means you just know recursive version, do it. Okay. Otherwise, people will try to avoid it. Okay. And I will show you some example. And of course, in here we have one example that people give us this formula, and we do computation. We use recursion, or we use the while loop. It's quite easy. Okay. But there's many application or many problem that we don't know how to solve the problem using for loop and while loop with if else. In that case, we have to use recursion. Okay. And later on, we will see people try to remove recursion. Okay, convert it into interactive way. Okay. Okay. Again, recursion it code itself with us to solve a smaller problem. Okay. Then some remarks: recursion is not efficient. Okay. We have to store intermediate argument. We have to store the rest, and the stack is the stack of the system. Where to keep track of everything like that have a limited limitation in the size of the number of recursive calls that we can make. Okay. In normal system, how big is your camera? We don't know, but we always have the limit. You cannot call like a recursive function 10,000 times. No. Okay. The system will stop you from that. Okay. Okay. We have another problem. Say just another example that people do the factorials. Now we just apply the function and then multiply by that. The function is recursive in a recursive form. And again, that's just to show you that we always have the base case, we have the recursive case. And the way we use recursion is only like that. The complexity will not change or even that higher in some case. Okay, and there is many application that people can change from like iterative. It means this using the while loop with iteration, and the say the recursive version. And you see here, if you back the binary structuring, you see the while loop here. We have lowercase, lower bound, upper bound. We divide by 2. We say if else, if this one is something we cannot find it, we check if it's smaller. Sorry. If we it is smaller, that we check our lower bound. And then you see that we change it to recursive method. The code will not be simpler, but that almost the same. Okay. Here, okay. So recursive actually based on idea and many like example, people try to use recursive because that is the solution, the way that people have to use in order to solve the problem. The idea normally from the divide and conquer strategy. Mean when we have some problem that is too big, a big problem or a problem, we don't know how to solve it. People try to say divide the problem into 2 parts, and then so that we have the smaller problem and then we can handle it. Okay, that is the idea. So it's just like in real life, if people ask you to count the number of like student currently in IU within 2 blocks, A1 and A2. So normally we cannot do it directly. We have to split it into 2 blocks. So say we assign one guy or just break the task. Say first task we count number in 1 block, and then the second block. And in 1 block is still big. We divide to multiple floor, and each floor we divide to multiple rooms, and we count the numbers. So divide and conquer is that way, means we try to do the application, solve the problem again and again with a smaller size by divide the problem into 2, or at least reduce the size. Okay, that is divide and conquer. And there is many example, many application based on that. And that is they have 2 famous example when people have divide and conquer that will show you in the following slide. In this case, now we have the Tower of Hanoi. Okay, I don't know how many of you know about the Tower of Hanoi problem. Do you know that puzzle already? Who knows the puzzle? Like if you know it, like if you know the puzzle. So just tell me how many of you know about that. Yeah, thank you, Minh. Just yeah, it's okay. Yeah, and the others, please tell me. It's good. It's good. It's good. Okay. And how about the others? Okay. Just if because not all of you know about that, let's try to do it slowly, one step by step, to explain to all to the others. Okay. So the Tower of Hanoi is the puzzle. We have 3 columns. Okay. And each of them have like this one is a placeholder, and we have 1 stack. Okay, it's like pyramid here, a pie of disk. Okay, the goal is to transfer all this from A to C. It's been one place to another. Okay, but we cannot just pick the whole stack. Okay, what we have to do is we we need to pick one dish at a time. Means one by one, and we cannot place the dish. We have to place the dish in order. Means the small dish should be on top of the bigger dish here. Okay, we cannot put it in the inverse direction. Means we cannot put it like this one. It is not valid. Okay, that is the rule. Okay, so you see that people have to do it, and when we have to move the dish from here to here, we have to calculate what to do first. Okay, that is the goal. And there is one solution. People show us that what to do. The idea is, the goal is to move the first n minus 1 dish on the top. Okay, this one from here. We have to move this one to some intermediate column, not our destination, so that the disk 4 is ready, available for us to move to the destination. Okay, so we move the largest disk from from the source to the destination. Okay, and then after that we move our subtree to the destination. That is the goal. Move here to B, and move 4 to C, and move B to C. Okay, and finally we solve it. And everyone, that is the algorithms. But of course, that is recursive. Means we cannot just move one big subtree from A to B. We have to form a problem from that. Means we apply the same technique. Means in order to move from 1 to 3 from B, from A to B, what we have to do is, in order to perform this one, we have sub-step here. Means we have to bring 2 and 1 and 2 to C. That is our task, and then we can bring 3 to B, and then we bring it back. Okay, and 1 and 2 we cannot bring it that way, so people did again. It means in order to move 1 and 2 to C, what we have is we have to move 1 to B and then 2 to C. That moment we have one dish to move, and then they doable. We can solve it. So you see, finally what we know is we will move A to B. They the first step. You see, in this case we have the algorithms, and we have to apply it recursively in order to know what to do. Okay, so everyone else, if you just want you to take some time to just play and practice with that. The idea is finally we try to see how we can implement it in the code. Okay, so let's say I have this 3 disks. I say we have 1, 2, 3, 4. Okay, we have ABC. I will try to make it smaller. 1 second, I will try to make it fixed. Fix to contain. Okay, so we have our disk like that. Okay, of course we can always increase it. Okay, so make it bigger a bit. Okay, assume we have our column like this, and our task to move, we have A here, B, and here C. Okay, so our task, I want you now, if you know about the algorithm already, I still want you to move it. Now my question is, I asked you to move 1, 2, 3, 4 to from A to B. That is the task. I want you to move it from A to B. Okay, so I suggest that everyone just do it step by step, like here. In order to move this one, I think the first step I have to do is to move 1 to C. That's it, and so far continue. Okay, so everyone just take some time and play with that. And to the one that you know about the algorithms, let's play with that. For the new for student who new to this kind of puzzle, take some time to think about this kind of thing, this kind of puzzle. Okay, at least you know the puzzle of Hanoi, the Tower of Hanoi, at least Vietnamese name. Okay, so take some time, everyone. If we have offline, it's been in-person class, I will make a game in class, but we cannot do it now. But anyway, please do it. If you want to check on the what, the algorithms, you can have a look at here, Okay, can you see it somewhere? Okay. So everyone, please take some time to play with that. It's good, and thank you. Hey Khang, it's not what we want, Khang, because you put it like how from step one you can move 3 discs 1, 2, 3 to C. It's not it's not a valid move. What we can do is we can only move 1 disc at a time. No? Okay, try to like put it in detail. Okay, from step 1 we just move 1 disc only. We cannot move like a block of 3 discs like that. Okay, for students that's not really like comfortable with this algorithms, what I suggest is we can do like this one. Let's say what to do. I try to put it somewhere. Okay. Now, what we can do is we can apply the algorithms. Say we have for this, like we have 1, 2, 3, 4. Okay. Now our task follow the algorithms. You remember we want to move 1, 2, 3. Okay. From what I try to perform something like. We have from A, B, C, okay? And now what we want from A, B, C, For the first step, the goal is to 1, 2, 3, 4 from A, no, to B. No. That is our goal. Of course, what people tell us as the 1.1 sub algorithm, we have to move 1, 2, 3 from what? 1, 2, 3 from A here to B, no? To C. That is the algorithms. And after that, we'll move 4 from A to B. Okay. And then last step, we have 1, 2, 3 from what? From C back to A. That's what we want. Okay. That is the algorithms. Okay. So now, when we have this one, it's not easy because we have three disks on top of each other. We have to do it again. In order to move 1, 2, 3 from A to C, what we have is want to move 1, 2 from A to what? To B. Okay, and then we move 3 from A to C. That is our subtask. And then we move 1, 2 from B to C. You see, that is the subtask. Okay, we have here from A to B to C. We can break it like 3 steps like that. And again, 1, 2 is not doable yet. What we have to do is we do again. So we move what? 1 from A to what? To C. That is the algorithms. And then we move 2 from here to B. Okay, and last step, we move what? 1 from C back to B. So you see, this step is doable. Right? This is doable. That is the algorithms. That what we should do means our very first step is to move 1 from A to C. 1 from A to C. That is what we do. Okay. After that, we move 2 from A to B, and then move back 1 from C to B. After that, we're done with this step. We move 3 from A to C, and so on. So everyone, you see, that is the way that we can do it, like step by step, and to apply the algorithms. Okay. And now, is it better for you, everyone? Everyone that is new to this proposal, is it okay? Quang Tùng, I don't think your solution is good. Yeah, it could be like that. Yeah. Yeah, what we have here, a thông. It's good, thông. Khang, your solution is not good, Khang, because you at step 2 you stuck 2 on top of 1. It's not good. And Wang Tùng, the same. Your solution is not correct, because somewhere in the second line you move 1 and 3 and 2. You make some mistake there, I think. Khang, your solution is not correct at step 2. Yeah, the solution of Thịnh is quite Thuận is quite good. I checking on that. 1, 2, 2, 3. Yep. Mm-hmm. 1, 2. Yep. It's good, Thuận. The others, is it better now, everyone? Do you need any further explanation? Mm-hmm. Yeah, 1. Long, you make a mistake, Long. We ask you to move the column A to B. Okay. Ngọc Long. Everyone, is it okay for you? Do you need any explanation for that? The others. Hello. Look. Hello. Please tell me. Is it okay for you? Okay. For other students, please tell me. Because what we want to do next is that 111. Here. This step. Okay. The goal of this 111 is mean 3-1 is that we want to move the stack of 1 2 from A to B. Okay, this is our goal, and in order to do that we apply the algorithm again. So the algorithm say that we will do the first n minus 1 disk, it means 1 from the destination to another place. Okay, so we move 1 to C so that we can move 2 to 2 to B. That is the goal. Okay, and after that we move back 1 from C to B so that we will have the stack 1 2 as the position B at the column B. Yep. It's good, Tuấn. Is it better now, Hải? Okay, everyone. So now let's move on. So we take a lot of time on this already because now, if you're really familiar with this, my question is, I want you to implement these algorithms using while loop and for loop. It's been iterative way without using recursion. Let's try to tell me what to do. It's better. You can check with the solution of the others. So, but everyone else. So now, as long as you know a bit on the algorithms, now I want you to implement it using while loop. Is it possible? For the moment, I would say no. You see, because we don't have the algorithm. It means we don't have the solution. We don't have the way to solve it using iterative like a loop. We don't know what to do first. Actually, what I have no idea what to do first. I have to like run it many level. It's been apply the algorithm step by step recursively in order to find out what to do in the first step. Okay, that is one concrete example. Like people don't know how to solve the Tower of Hanoi using iterative methods. It's been while loop and for loop. And then we are forced to use recursive. Okay, everyone. So now let's back to the slide and try to see how we can do it in recursive way. Try to erase it. Now, for a recursive method, you will see that in this one, is it not, let's say, that easy as you say, or the recursive method will easier for us to know, to read, because sometimes it's not straightforward. Let's say now we have the Tower of Hanoi. Okay, we need a function to solve it. We have 3 columns. Okay, we have number of this here. We do it recursively, and we have the base case. This means if we have only one element to do, what we say, just move this one from one location to another. Okay, that's easy. Okay, because if you want this only, we just move it, okay, from one position, from the form to the destination, from A to C directly if we want. We have no problem with that. Okay, now if it's not, so here the way we write the recursive methods is directly just rewrite the algorithms in the code. Do the tower, we say remove the n minus 1 this. Okay, say n minus 1 here. Now we want to do, which means we solve the problem again, but we change the order. So we have here A, May, and our destination is not C, but we want to change it to B. The intermediate is B. Okay, see? And the first column we form, the last column is the destination. Now we want to move n minus 1 tower from A to B. That's what we want. Okay, see if you check this, we want from A, sorry, I'm sorry. So we have here so A to B, and we use C at the intermediate. That is our task. Okay, and after we move the top one items, and you see here, that is what we say, we move 1 minus n minus 1 from A to B. That is what we want. And after we do that, we're done with that, we move the biggest the disk number 4 from A, okay, to the destination. Okay, this is what we want. This is C. Okay, and then we just do n minus 1. It means the stack we move from B, from the intermediate B, okay, back to the destination C. Okay, and you see that is the way that we implement the recursion. See, it's just straightforward, no? Directly from the solution we have at hand. And we have the base case and we have recursive case. That's it. You see? That is the situation. That is where I would say we have to use recursion, because that is what we know. And we have no other choice. We cannot use the for loop and while loop. Okay? So that's it. That is the Tower of Hanoi. So everyone else, please tell me, is it clear? Do you have any question on this? Yeah. The others, is it clear? The way people do recursion. It's just straightforward, no? It's just exactly what we do, what we know for the order. And that's it. Okay? And now, if you don't have any other question, you say, my next question for you is, do you think that we can convert these algorithms to iterative way because recursion is not good? We don't want to use recursion. Can we do it? Can we convert this recursive method to an iterative method? Yes or no? If you say yes, just show us the hint. Okay, like the way to do what should we do? What can we do in order to make it iterative? Yes, that's good. So, but this moment I want to say is that people know that recursion is not good, but we have to do it. We have to do it. Now, after we have the solution, we can run it. Now, what people try to do, and they have the algorithms. So, it's to convert this recursive one into an iterative way using stack. And that is the task, and that is the thing we will see in the end of this section. Okay, means that for all recursive method, people can always make it iterative. Okay, they have the way to do it. Okay, but based on the current version of the recursive method and apply some techniques we'll see in the end of the section. Okay, so that's it. Now let's move on. So we've been spent quite a lot of time on this already. Now we want to move to this one. What people say is now we try to show you one algorithm. We name it merge sort. Okay, this algorithm is like have a better performance. It is n log n. See, if you remember, the difference will be log n versus n. Okay, And log n is just like the linear shape versus the binary shapes. Okay, so log 12 and log. I think that is good. It's quite good. It's very good if we compare n versus log n. Okay, so here we can reduce the complexity somehow. Okay, this is based on one of the observation. Do you remember in lab number 1, I do ask you to do something, we call it merge two sorted array. Did you remember that? Do you remember that? When we have to merge two sorted array in order to make a new sorted array from the two given array, what can we do? What do you do? Yeah. There is one exercise quite important just to show you that when we do that kind of thing, you can feel something, no? You feel that now people can sort two sorted array somehow in a very efficient way. Now, if we just do it in a simply like a naive way, we put all of the element of the first array to the destination array like this, and we put it here, the second array to the end of the destination, and then we can just apply the sorting items. That is one solution, but the complexity is we need n step for the copying and n square step for the sorting. Okay, in general it will be n square at the complexity. It's not good. What people can do, if you remember, tell me please, what should we do? If we have sorted, it's been in the increasing order already, here in the increasing order, what should we do? What should we do is, we try to compare the first element here. We need two pointer. The first pointer here and the second pointer here. Okay, we compare the value at the pointer. So let's say this one is smaller, and we take it. We put it here with 7 here. Okay, as you see, there is number 1. And after we take it, we move it here. We move our pointer to the next position. Okay, and now we compare again. We compare the pointer, the value at this pointer is 14 versus 22, 3. It's again smaller, and we just put it here. And then we move our pointer to the next element. We compare. See? And this one is bigger, so we take this guy. After we take it, we move the pointer to the next. So we have now compare, sorry, this 47 and 39. So this is smaller, we take it. Okay, so we move our pointer to the next position again. So we have it, and so on. Okay, you see that way. Have a look at the number of copy. For each element there, we have to copy exactly 1 time. After I copy it to the final destination, I will not move it. I copy 7 here, I will put it here. I will not move it. So it's just in one copy, I put the number in the good position, in the correct position. And with one comparison, for each comparison, I can make one decision. Okay, so it means for one comparison, I can put one item in the right place. It's just briefly the sense that, you see, it a lot more efficient than buffer sort and selection sort if we have two array in sorted order. Okay, that is the thing. Okay, now people try to apply this kind of this observation to the sorting items. Please have a look at this, and after that we have break. Okay, the idea is people try to divide the array into two parts, and after that we divide again until the moment we have our subarray just two elements. Okay, you see, if we have two elements, the first element is sorted among itself and the second is sorted. Okay? Means that we have two things and just put it here, and we sort, we compare, and we know where to put it. We put it here and here, and the same goes there. In this case, we're lucky, we don't need to swap anything, we just put it here. Okay, and you see, following that way, so we have two sorted array with two elements here, two element sorted array, and then we compare and put it in the right position one by one. So you see, this is merge sort. It's quite, say, straightforward. We divide by 2 every time, and finally we have the array of one element or two, and then we just put it in the right position. Okay, and do the merge for the higher, like the dimension, it's been bigger the array. And finally we have two 4-element subarray. They sorted. Now just compare and put it in the right position, and that's it. Okay, so you see, that is the thing. Okay, do you see that quite straightforward and easy? Now what I want you to do is just think about that and think about these algorithms by just try to do the sorting. Okay, so we have this kind of array. So please try to sort it. Okay, and after you finish the sorting, you can take 20-minute break. Okay, we will back with, say, to analyze the complexity of this guy. Okay, now just try to sort it to see how easy it is. It means how many number of operation, compare and swapping we have to do, or copy we have to do in order to sort or to put given in data in the right position. Okay, so sort the data, sort this item, okay, and then 20-minute break. Okay. Okay, everyone, then see you. Okay. Okay, so welcome back everyone. So you see that now I will back to the sorting items. The result from Kang is that correct Kang, so now. But anyway, now you see that the way we do the merge sorts based on the observation that if we have two sorted array, the way that we can form the merge array of the two in order is simpler than sorting everything from scratch. Okay, that is the observation, and then people have it like this. Just divide this array by 2, and again until we have only one element. Okay, please note that if we divide things by 2 every time, so that will be, so can you tell me if we have a say number 16, we divide by 2 until we reach 1. So how many steps we have to do? How many times we have to divide the result? Okay. And for number n, if we divide by 2 until we reach 1, how many steps we have? Thank you, Ying. If we have numbers, let's say, yes, that is the thing. Everyone, when we divide until we reach 1, there is log n. Okay, that is the hint that we can check on the complexity of these algorithms. Okay, if in the algorithm somehow, this is just the hint now, it's not exactly that, but the hint. If you see that the algorithm try to divide the problem into 2 anytime, so we have the log n somewhere. Okay, so that is the hint to analyze. Of course, when you have to like analyze the complexity of the algorithm, is not easy. It's not easy. Okay, for basic algorithm, sample algorithms, it will be straightforward, but most of the time to identify the complexity of an algorithm is not easy. Okay, it's mean the exact complexity. Okay, but anyway, that is the merge sorts, and we will based on that hint to check on the complexity of this one later. Now let's have a look at the way that people implement the merge sorts. Just 1 second. Okay, now, so what we have, the merge sorts, as you remember, we divide by 2, we sort the 2 subarray, and that's it. No, so here is the algorithm that express exactly what we have. So we have the upper bound and lower bound. We have the mid. It's mean the lower bound, upper bound here. We do the what? We do the merge sort, lower bound and the mid, merge sort, the mid and the upper. Okay. And after we merge 2 sorted array, a subarray. What we do is we merge them. Okay. What we do is to merge the array, and the mid is the one to tell us what will be on the left side and on the right side of the data. Okay, and then here for the merge function, the merge function is like exactly what you know. So we have a thing here the low pointer, the mid, the higher pointer is mean the above. This is the one that have us to separate the array into two parts. No, the low pointer is for the first half of the array. Higher pointer will be the second half of the array. And then we try to check. That is the thing that you should remember. We check the data in the original array, it means the array, compared, okay? And if it's smaller and lower, we copy it into the workspace, okay? As you remember in the merge sort, we need to, as you hear, see, we need to, we will not modify the data of the original array, but we copy it here to the destination array C. Okay, so the merge sorts, the merge do the same. We have the array, but we copy it into the workspace. Okay, and then if one of the array reach the end, we copy the others to the rest. It means if we merge the array, but one array longer than the other, we just copy the remaining to the destination. And finally, after we have everything, we just say copy the data from the workspace back to the original array. No, that is the algorithm. Okay, so we have two subarray. We consider using index, and in order to merge, we copy the data to a workspace, and then we copy it back to the original array. Okay, so that is the algorithms. Okay, and you see here the way we do. There is one thing now that you should remember, very important to this for this algorithm, is that we need a workspace. Means that this algorithm we need extra memory. If we have an array of 1000 elements, we must have an extra 1000 memory slot in order to run the merge sort algorithm, because we have to copy the data there and then we copy it back. Okay, see, that is one of the ways, as I mentioned you many times, is that people can reduce the complexity of the algorithms by using extra memory. Okay, in this case we use an extra workspace. And finally, we can reduce the complexity from n squared to n log n. But of course, that will be a drawback if we don't have enough memory. Let's say you have one hard drive of 1 terabyte, okay, and then you want to sort on item in that array, in that hard drive. Using merge sort means that you need an extra 1 terabyte hard drive. Okay, see the problem? Okay, so we see that is the thing. Okay, it can help us to reduce the complexity, but we have to increase the complexity in space. Okay. Okay. Is it clear, everyone? Any question on this? Yep. It's good. Okay. And now let's try to analyze the the sorting algorithms. Okay, when we have the algorithms in the merge sort, what you see is that we have two basic operations. The first one is compare. No? We just divide. Divide is just the step in logic. We will not do anything with the data. And then finally we reach one element. Okay. Then we do the comparison. And after we compare, what we do? We copy it to the workspace and then copy it back to the origin. Okay, that is it. So the operation, the complexity of this algorithm is actually can measure by the number of comparison and the number of copy. Okay. So how many copies do we have? So for each things like this, what we have, we have this data. Each of them, we will copy it to the workspace. Okay. One time in this level, it means that the lowest level of the subarray is the array of two elements. Of two elements. And then the array of 4 elements, then array of 8 elements. So check on that. We have A, and then 4, and then 2. The last level is 1. We will not count it. Okay. So you see, every time we divide by 2, there are the algorithms. So how many levels do we have in general? So we have n. Sorry, we have log 2 of n as a number of level. No? Log 2 of n is the number of level that we have for this level. We have 8 is 1, 4, and 2. 8 here, 4, and 2. Okay. And at each level, we have to work with all elements. No? For level, the lowest level here with 2 elements, we have 4 pairs of that. Okay. So we have n element. And for each level, we copy it n times. So we have log n level. So here is the number of copy. Okay. Because we have to copy from the data back to the workspace and back. We may say 2 log 2 of n. Okay. But here what you say, if we have 2 elements, we copy 4 times. 4 elements, we copy how many? 4 log. So we copy for 4 elements, we divide by 2. We have 2 levels, level 4, level 2. For each level, we say copy number of copy into workspace, and the total number of copy we multiply by 2. Okay. So that is number of copy. And here in the max and min means that the max and min number of comparison. For each level like that, we have to compare between elements. Okay. Now we reach around like 2 times, few times for the comparison. People just count it like this. Okay. But in general, it is smaller than the number of copy. Okay. And for complexity, people will say the complexity will be n log 2 of n. Of course, we can say log 2 multiplied by 2 n log 2 of n. But if n is big enough, we can remove 2. So the general complexity of the algorithm is and log n. Okay. Is it clear, everyone? Okay, see? Any question on this? Okay. Great. Thank you. And the others, is it clear for you? You see, that's one of the way people can improve the sorting algorithms. Okay, and this approach, say we use extra memory, so we can reduce the number of steps. Okay, so and that's it, everyone. That's it for the merge sort. Okay, it's quite simple, no? It's quite basic. And then now what I want you to do is, we are now moving to the last part of this section. We try to say again is that recursion is not efficient, okay? And because we have the algorithms, because they are naturally in recursive form, means that the way that people define the solution is using recursive definition. Okay, then we have to do it. That is the reason why people say, well, it's not efficient, because we're forced to do now after we have the solution, try to remove recursion. Okay, so here is actually the way that people can do in order to remove recursion. Say that actually when people let's say do recursion in the memory, in your operating system, it will manage a stack of function call. Let's say we compute for some numbers, like from triangle, we start with number 4 here. So they will have the function name computes 4, and they keep the value of the variable n is 4. And inside the 4, you do something, and you continue to work with the smaller size, not smaller problem, and compute 3. And the system had to make one copy. And in here, in the stack here, they will store where they should return after they finish the compute 3, and so on. When 2, they will store where they should return when we finish the compute 3, and so forth. So behind the scene, the system will use stack. And based on that observation, based on the way that your system, your operating system, use stack to handle recursive method, people just apply that kind of thing directly to remove recursion. Okay, and normally people will organize we use a stack to say that will be the list of things we have to do. Okay, so every time we want to move to another function, we will store the rest of the last, like executed, last command, last instruction have been executed, so that next time we can return back to that. So in that moment, we need the rest of the last executed function, that will be the stack. It's been the last one that executed, put in the stack, will be the first one we will use to return. And that is the idea. So everyone else, now I really want you to spend time to read on this one. There is one algorithm on page 284 in the textbook that will tell you how is one of the algorithms to say remove recursion So now I want you to spend time to read on that, and I will say break you on into a breakout room now, so that you can discuss with each other to read about like how to remove recursion with stack, and later on you will try to let's say present it to everyone. Okay, so now how do you want to like form a team for a breakout room? You want to make it random, or you want to work with your team? So I prefer to make it random. What do you think about that? It's just random. Okay, so they had chance for you to say work with each other. I will make a team of 4 to 5 people. Okay, so everyone please do it. Thank you. Phong and you, why you are here? Okay, everyone. So I will on back. So everyone, so welcome back. So we are like out of time, but everyone, there you think that you try to read the document on to remove recursion, but the idea is that there are two ways to remove recursion. The first one is to simulate this corn stack of the operating system, okay? And the second way is we use the stack as a to-do list, okay? So please again at home rework on that, okay? So there is two. There are two ways to remove recursion. One is to simulate corn stack. Second one is to use stack as a to-do list. Okay, so everyone at home, so please do checks on this kind of thing. Okay, and next time I would try to explain it to all of you in detail. Okay, otherwise that's it for today, everyone. Thank you. Hope that you had the starting point for reading. Please continue reading and discuss with your teammate in the breakout room. Okay, so otherwise you can leave now. Thank you. Yeah, goodbye. Thank you.